So now we are going to start the quantum AI lab session. Of course, the lab session is coordinated by Abderrahman Abdelkarim, but his mic, he's not in a good environment at the moment. So I'm gonna start. So thanks, Abderrahman, for coordinating the lab and coordinating the session. So today we are gonna covering the quantum phase estimation. Last time we covered quantum Fourier transform and how we use it to map two domains together using quantum circuit. So quantum phase estimation contains quantum Fourier transform as an essential element in the algorithm itself. So I'm gonna briefly summarize a quantum Fourier transform, and then we step slowly to the phase kickback, and then the quantum phase estimation. I'm sharing my screen. Okay, so last time we have covered the quantum Fourier transform is actually a translation of the classical Fourier transform using qubit representation or the Hilbert space representation to the quantum Fourier. Yeah.
The only thing that's showing up is just a white. There's nothing there. We can't. I mean, if that's what you're showing, that's fine. But I'm just saying that we're not seeing any text or images or anything. It's just white.
Oh yes,
white.
Greg. I'm checking it. Yeah, thanks. I'm checking now why it doesn't appear.
Of course.
Yeah. No. Yeah. Thanks for the note. Now it starts to appear. Yeah. Yeah. Thanks. And please let me know if I have a glitch or something doesn't work during the session. So that's really much appreciated. So now it's for the quantum Fourier transform. It's a translation for the classical. So the classical that if we wanted to go to another domain represented in a kernel Y, we do this transformation. So we get 1 over root square of n sigma from x equals 0 to n minus 1. And then we have exponential 2I to pi. Then we have xy divided by n. And then we have f of x. So with this, we can transform any function representation represented on a grid or a sequence of a grid of x to another representation in y. So that's what we do. So the Fourier transform preserves this, and it is a very powerful transformation. Even Schrödinger equation could be derived from a Fourier transform. So in that sense, if we wanted to express it in a matrix representation, this is what we do. We have a vector of this function, and then we have a matrix, and then we have f. This is f of x. This is y. This is a representation in x. This is a representation in y. Similarly, if we wanted to do it in quantum system, we can just say, okay, we have a new state phi. That state phi would equal to a matrix called the quantum Fourier transform acting on a state psi. So we transform our state from this representation to another representation phi. This would mean that we have UQFT, the matrix. So, and then we have the representation from x equals 0 to 2 to the power n minus 1, where n equal to 2 to the power n is the number of qubits. So this is f of x, and then we have x, and then f of x is just the amplitude of the state. So for example, psi is represented as sum from x equals 0 to 2n minus 1 f of x. This means that we have f of x1, let's start from 0, x0, plus f of x1 plus until we achieve to f of x 2 to the power n minus 1 and x 2 to the power n minus 1. So this is state vector. In a nutshell, this is state vector represented in a space. We have a space here. Of course, it's not orthogonal. And we have x0, x1, x2, until x2 to the power n minus 1. And then we have a representation of psi. And then we transform from this representation to another representation, which has y's in it. Then we get phi. So that's what we do. So the Fourier transform does this mapping for us. Hence, we can conclude that f of x, since it is the amplitude, it's just as a projection of the state vector on a specific dimension or on a specific state. So we see here that this vector psi is composed of projection on the dimension of the Hilbert space. So all of these add up to a big space called the Hilbert space, and then these amplitudes are the projection of psi on x0, for example, that f of x0 is a projection on x0, f of x1 is a projection on x1, and so on. And then since this is a projection, we can write it as just shifting the page. So the bra of x times the kit of psi gives me this amplitude. So this is a projection of psi in the dimension of x. So if you wanted to represent this in a vector in 2D, so the projection on the x-axis is this one. So we can write it like this, xa. This gives me this part. Now, since we could have done this, we can now write a phi. And please stop me if you have any question. We can write it finally as 1 over root square of 2 to the power n, because this is our n, sigma x starts from 0 to 2 to the power n minus 1. And then we have e to the power I to pi xy divided by 2 to the power n. And then we have x psi. And then we have our x. So now that's what we have. So this is our amplitudes, and then we can write that the amplitude of this one, which is Fy, will equal 1 over root square of 2 to the power n, sigma x starts from 0 to 2 to the power n minus 1, e to the power I to pi xy divided by 2 to the power n, and then we have f of x. So after all, the take-home message here, we go from one domain to another, even quantum or classical. The only trick here that we need to pay attention is that The quantum register doesn't understand the decimals. So if x and y are decimal, it's not understood, this coefficient. So we have to use a binary representation. And this is why we do another trick, which we have shown last time. And this trick is that we represent this phase as, yeah, please, Greg.
You said that quantum doesn't understand, and then you said a word. I didn't understand that word. What was that?
The decimal representation of
Oh,
number.
decimal. Okay,
Yeah,
I'm
the
sorry. Thank
decimal.
you.
Yeah,
Thank you.
yeah,
Thank you.
yeah. Thanks, Greg. The decimal representation is not understood. This is why we transform into binary. And if we go to binary, we do like something like this. So if we have a number, like for example pi, number pi, then what we do is to transform it to binary, and then it means that we write in this format. So in that sense, our Fourier transform will be something like this. The exponential will be e to power I to pi xy divided by 2 to the power n. This is, we derived it last time. We end up with something like this, e to I to pi yk 0 xn minus 1 xn minus 2 x1 x0, and then we loop over y. So that's the whole idea. The y and the x are represented in binary representation. So the only thing, we need to loop over this. So if we have a number in binary 0 1 1 0 0 1 1 0 0 for x and y, we need qubits to represent both, and then the quantum Fourier transform will work fine. Okay, so this is what we derived last time. The take-home message that when we achieved, let me just give an example. Just avoiding the complicated examples. Okay, so now let's have a 2-qubit system. In the 2-qubit system, we have n equal 2, means that the size of my Hilbert space is big N equals 2 to power n, which is 4. So now this is the size of it. The bases that I can use are ket 0 0, ket 0 1, ket 1 0, ket 1 1. Those are the bases. Then now the quantum Fourier transform matrix will act on this on the bases in a sense that I will have half ket 0 1 0 0. So it means that this is how I load it on in the binary, plus e to power I 2 pi 0 x1 x0. Then I have here 0 1 plus e to power I to pi 0 x0. Here 1 0. plus e to power I to pi. Let me write this alone because it's a big term. Zero point x zero plus 0.x1 x0 times kit 1. So what's happening here? I have 2 qubits. I'm now loading them on the binary. If I expand the expression of the Fourier transform, I end up with this one, the one that we derived. You can find it also in Wikipedia. So we expand it like this. So the first thing, we have nothing, no phase acting on the 0, 0. The phase only appear when one of the qubits is loaded with binary digit 1. And this is why we have this. We have the phase, and then we have the binary representation of the number. So the y here, the y here is 0. So this is why we don't have a phase, because 0 times any number exponential to power 0 will equal to 1. So this is why we have no phase here. Now the y is 1. So okay, so we have phase and so on. So that's how we derive it. So now this will give me as a final expression, I will get half get 0, 0 plus e to power I to pi x1 and so on. Okay, so the take-home message here, to achieve the Fourier transform, I will need two things. I will need a gate that can create the superposition because I have superposition, and then I need a gate that can apply the phase. And the gate that can apply the phase is a controlled phase gate. So the controlled phase gate can do this job. So I need two components. I can repeat them as much as needed for the number of the qubits. So here I have 2 qubit system. So I will need a Hadamard gate to create a superposition. And then I will need a control phase gate to apply these phases. And then I will need a Hadamard gate again to create the second part of the superposition and so on. So depending on this expression, I just create as much number of as I need from gates. So this is what we have seen last time, that you can just retrieve this circuit from Qiskit or anything, but now you understand the logic that we need a superposition, two of them. So this is why we need two Hadamard in this example, and then we need a control phase gate to apply those phases. So this is regarding the quantum phase, the quantum Fourier transform. Now, I'm going to elaborate more on the quantum phase estimation. So this is the quantum Fourier transform that has been explained last time in detail. Now we are going to jump to the quantum phase estimation. And first, to study this, I would like to mention what we mean by a phase kickback. So before I step in, I would like to ask Abderrahman if this was already explained before. If yes, I can only summarize it briefly in 1 or 2 minutes. Okay, let's summarize it quickly. The phase kickback, it means that it's a quantum phenomenon that occur when a controlled operation, it changes the phase of the control qubit. So I can have a control matrix, which will be identity 0, 0, and matrix U. And this is 4 by 4 matrix. This is why I make here this double bar. It means that I have 2 by 2 matrix. So it's a matrix, is not a number. And then if I have a controlled U acting on 2 qubits, where the first qubit is the control, the second one is the target, then the phase kickback would mean that I get a phase when I act on this one. So let's see, this is my target state. And the CU will act on psi, then I get something like this. So now I get alternation to the phase. Okay, so we're gonna see an example of this shortly. Now there is something important we need to pay attention to. There is rotational gates that we use quite often in quantum computing, and pretty much anything in physics can be derived from rotational gates. Even special relativity, you can rotate a frame and so on. So if you have a Bloch sphere, then the rotation around the z-axis can be given by rotational matrix Rz of theta, which is e to power I theta divided by 2. I can put minus here, e to power I theta divided by 2, and then I have 2 zeros. This is my rotation. This is a matrix that I can use to rotate a vector around the z-axis. Similarly, I can rotate a vector around the y. So I call it Ry of theta, and this could be cosine theta over 2 minus I sine theta over 2 minus I sine theta over 2 cosine theta over 2, and so on. Why I'm mentioning this is just to keep in mind how these rotational gates are doing. Any gate pretty much used in quantum computing can be decomposed in terms of rotations, like a combination of rotations that act in a sequence. This will produce for me a specific gate. And this actually what sometimes might yield to a noise, because to apply this rotational gate, each angle might contain a small error. So if you want to have a theta precisely to be 5 degrees, then if you have a small error in it, then your rotational gate will inherit this error. So whenever you update the parameters of these rotational gates, which are those thetas, then there is some minute error that's associated with it, and this is what sometimes induce the noise in the quantum circuit. Okay, so this is a review on the rotational gate. Now let's see the phase kickback, how it happens. So if I have two states, this one has a relative phase. this relative phase I cannot omit. It is very important to keep this phase. So the information is really intact in this phase. So this is contains the phase information of the quantum state itself. If I have this specific state, and then now I have 1 over root square of 2 e to power I theta, then I have 0 here, 1 here. This is now called global phase. So it's important to see now, this is relative phase, this is global phase. Why it's global? Because it's outside the ratios or the relation between the 0 and 1. So if this one disappeared, it won't impact any information that I have regarding this. And if I use a normalization, this phase will disappear. So this will disappear in the normalization. However, here it doesn't disappear. It influences the relation between 0 and 1. So the relative phase is important because it contains some information about the relation between the 0 and 1. So it preserves quantum information inside this phase. However, if I have a global phase, it doesn't matter, it doesn't impact my quantum state. Okay, so how now the phase kickback appears? If I have this specific circuit, with a controlled U here is actually RZ, then this U matrix will equal to RZ of theta, which will equal to 1, 0, 0 e to power I theta. That will equal to 1, 0, 0 cosine theta plus I sine theta. Okay, so do you follow this? Or? Okay, so that's great. So now let's check the action of RZ of theta acting on ket 0. If I do that, I will get the same ket 0. So you can evaluate it by hand and check if I got it correctly or I had a typo, but this is the action. If I have RZ of theta acting on 1, this will give me cosine theta 1 plus I sine theta 1. Okay, so now this is the action of this rotational gate on these bases. So this is the action on the 0, this is the action on the 1. So if I have a qubit in one state, this is the action I see of the RZ of theta. If I have the qubit in 0, this is the action I see if the qubit in ket 0 state. Okay, so now let's see how the phase kickback appears with me. So if we see here what happens, now the initial state is actually ket 0 tensor ket 0. This will give me ket 0, 0. So this is my initial state of the 2 qubits. Now I will apply Hadamard gate on the first qubit Q0 and then X gate on the second qubit Q1. So if I do that, I will get H acting tensor X acting on the ket 0, 0. This will give me H acting on ket 0 tensor x acting on kit 0, then I will get 1 over root square of 2, kit 0 plus kit 1, tensor kit 1. What happens here is that the Hadamard gate creates for me the superposition. The X is a flipping gate, so this is flips the bit of the qubit from 0 to 1. So I will get here 1 over root square of 2, kit 0, 1 plus kit 1, 1. So this is a result of the action of these two gates. Now I need the third step is the action of the rotational part. So the action of this one would mean that I have CZ control the CZ acting on this will give me e to 2 pi. This is not CZ, this is just controlled RZ. This is will give me kit 0, 1 plus e to power I phi kit 1, 1. Okay, so this is the action of this gate. This action produced for me a phase, and this is the phase that has been kicked back into the target qubit. So the second qubit got this phase. This is why we call it phase kickback. So the state is unchanged, we only got a phase, extra relative phase. Okay, so why this is important? Because it's relevant to the quantum phase estimation. We need to induce sometimes this phase inside the state. So now we understand that this parameterized gates, these rotational gates, can cause or produce a relative phase here in this specific circumstances or situation, and this is a phase kickback. It is a relative phase that's important, so I cannot destroy it. It is very important because it has quantum information in it. It expresses a relation between these bases, so it has quantum information. It's not a global phase which I can get rid of, or it doesn't impact my quantum system. No, it is a relative phase which it's important for the quantum system. Okay, so hopefully this is clear. Okay, so does anyone have any question? Yes, and this is what we are gonna do now, Abderrahman, in the next slide. So that's a good remark. Okay, does anyone have any question? Okay, so if not, let's proceed with the quantum phase estimation. So as Abderrahman said, the idea that of quantum phase estimation is that we can use this phase to relate it to the eigenvalue or to the eigenvalue problem of a given vector. So let's see the following example. Quantum phase estimation. Now, if I have the quantum phase estimation, I can have an operator U. It's a matrix because it's a Hermitian matrix. This operator will act on a quantum state psi. Then the eigenvalue of this will be giving a scalar vector called lambda times the same eigenstate. So this is my eigenvalue. So these eigenvalues is actually the solution of the characteristic equation, which we have it as a determinant of u minus lambda I. And u here is a unitary operator. Now the trick is, if the eigenvalue, this one, so now let's write this equation in a big format. So I have u acting on psi, so equals to lambda psi. If I can represent this one as a phase, then I'm pretty much can use quantum algorithms to find the eigenvalues of this. So the eigenvalue can be represented in this phase or multiple of this phase. So like e to power I to pi theta, and theta is from 0, 1. If I can use this and I can represent theta in binary format, then I'm pretty much can compute the theta as we have seen in the quantum Fourier transform. If I can get this binary string, I can get the decimal value, and then I can compute the eigenvalue problem. So I will get theta will equal to, let's write the, okay, I'm just also the beginning of the page. Yes, now it's here. Or I to pi theta will equal to e to power I to pi. We have sigma I starts from 1 to from 0 to n 2 to power n minus 1, and then I have bi 2 to power minus I. Okay, so this is my binary representation, and then I can find this basically. Okay, before we proceed to a numerical example, I wanted to highlight what we use, or what is the added value of doing this. So the quantum phase estimation is very helpful because it actually helps if I can define my problem in terms of an operator acting on a state, and then I get eigenvalues. Then I can pretty much compute any eigenvalue for any problem. So that can help in finding the energy eigenvalues. It can help in general in eigenvalue problem in chemistry and the material science. It can help also in solving quantum linear system algorithms like HHL algorithm. So it's very helpful. And this also has wide applications that can extend it to Shor algorithms and other powerful algorithms as well. So the quantum phase estimation is leverages the power of estimating the phase. So you can induce a phase via the phase kickback, and then you can compute this phase by assigning this phase to quantum register. And then if you got this binary string, you are sort of getting the phase. Okay, so now let's answer the following question. How we can estimate a phase of a unitary operator u acting on psi equal to I to pi theta acting on psi. We would like to estimate this one. So now the answer is we can create a quantum circuit of n qubits. And in this quantum circuit, we are going to use UK number of gates, as we have seen in the quantum phase estimation, and then apply it k times. Let's see how. So if we have U acting on a state psi, then U has a size of 2 to the power n times 2 to the power n. This is the size, and the size of the vector psi is 2 to the power n. Then now we have U1 acting on psi, that will equal to e to the power I to pi theta acting on psi. If we have 2 to the power 2, then we just square this one, so we get e to the power I to pi theta times e to the power I to pi theta, and then acting on psi. And this means that I get e to the power I 4 pi theta acting on psi. If I use U3 acting on psi, this will give me u to the power 2 acting on e to the power I to pi theta of psi. That will give me e to the power I 4 pi theta times e to the power I to pi theta acting on psi. And this will give me e to the power I 6 pi theta acting on psi. So we get a general rule here, which is u to power k acting on psi, that equals to e to the power I to pi k theta acting on psi. So as many as the values that we need to obtain, we can just apply these control gates as we have seen in quantum phase estimation. So we get a circuit representation. That's like this. And this means that I apply this U as much as I need to represent the phase. Okay, so now let's see. This depends on the number of the bit representation of theta. So this is my phase, e to the I theta. So if theta is represented is in 0, Pn until B0, then depending on this number, I'm gonna choose the number of the qubits. So let's assume I will represent theta with 1 bit only. If I do this, then I get m equal 1. This is the number of bits. Then my circuit will be the following. I have Q0, and then I have my state psi, the one that will contain the operation. So I act with a Hadamard gate to create a superposition. Then I apply u to the power 0, because I only have u2 to the power 0, because I only have 1 bit, so I need only one operation. And then I apply the inverse of quantum Fourier transform, and then measure this one to obtain the bit. If I do that, I get 1 binary bit to represent the theta. So if I do the action on the qubit, the Hadamard gate, will create superposition, as we have seen before, and then u to 2 power 0. This will act on the second qubit and controlled by the first qubit, which is a 0 qubit, and then I get something like this. Then the final state, if you work out the math, will be like similarly, if I wanted to do it for 2 qubit, I'm gonna share another screen just to show you the general case. Okay, so this is for m equal 2. So I have 2 ancilla qubits. Those one are used in the binary representation, as we have seen in the quantum Fourier transform last time. So I have 2 qubits. I need 2 digits to represent the theta. So I use 2 ancilla qubits, and then typically the psi will have also more bits, more qubits in it. Then I will get the Hadamard gate to Hadamard gates, create a superposition. Then I have 2 control gates, u to power 2 to 0, and then u to power 2 to power 1. And then I apply here the inverse of the quantum field transform for 2 qubits. I measure, I get the binary here. Then I get the general case. The general case for m bit, you need m ancilla qubits, and then that's what you get after all. So you get something h, and then you apply all of this operation as much as needed. You use the inverse of the quantum field transform to disentangle the qubits, and then you measure, and then you get the bits. And then depending on the precision, if you need 16-bit of precision to represent your theta, then you will need 16 number of qubits, and so on. Okay, with that, we have seen the quantum phase estimation. It's actually to estimate the phase, which is the eigenvalue. And to estimate the phase of the eigenvalue, I need to specify the theta, to obtain this theta. So I do this quantum circuit, I measure to get the binary representation of this theta. I can convert it to decimal representation later. So if it is decimal, then I get it as a decimal representation. And then this will be, if I evaluate e to power I, the decimal representation of theta, then I get a number. This number will be the eigenvalue of the problem. Okay, so do you have any question? Okay, so with that, I can conclude the theory session. This will be clearer with Abderrahman when he explains the practical session. So this will be clearer. This is just a rough idea about how the theory is being developed in this. But of course, when we go to the practicality, we see now we need this amount of number of ancilla qubits to represent the binary representation of theta. We measure, we get a binary string, we convert it to decimal. Once we convert it to decimal, we get a value. We evaluate this number, e to power I theta. We get a number. This number will be my eigenvalue. So that's and this is a sort of the logic in quantum computing. We only try to project the classical thinking into quantum, which is sometimes time consuming in some of the algorithms because it's not native. We have to go from decimal to binary representation. However, for quantum phase estimation, it is pretty straightforward. So any simulation that leverages quantum phase estimation, it uses this power of assigning the phase kickback. So if I can compute this phase kickback, depending on the number of qubits for the precision, then I can just pretty much do everything. So that's a powerful representation. Yeah, please, Greg.
Are you about done with your presentation then?
Yes, Abderrahman is gonna now present the notebook.
Okay. Well, I was going to ask some general questions about phase,
Yeah,
but if
please.
you've got other things to talk about, I won't go into that at this time.
Yeah, please ask.
So no, what I was going to ask is to help me get my head around phase. I mean, I understand the math. I mean, I could do the linear algebra that you're doing easily enough. That's not the problem. What I'm saying is, share with me your understanding of how the phase then interacts with the data storage within the qubit, where it relates to possible the gates and measurements and so on and so forth. How would you express that to someone that didn't have? I guess it would be another way to express it is how would you express that to someone that doesn't have the physics background? What would that represent, say, on a box sphere or something?
So that's a good question. I'm gonna just share this window quite quickly. So the whole idea is that we got from the phase kickback, we got a state similar to this one. And this is on Bloch sphere. This is a relative phase. So with this one and this one, this will give me a vector. So this theta can be induced by a rotation. So if you have a vector that rotates, then this phase represents how this one is related to 0. So this is 0, this is the 1. So the vector here, whatever its location on the Bloch sphere, is assigned by this ratio between the 1 and the 0. So we choose to represent it as e to power I theta. This is our choice. If we make those equal, so we say, okay, it's 1 over root square of 2, 0, plus 1 over root square of 2, 1. Then we get the Hadamard, so this is x, so we get something here, for example. But now we don't want this. We wanted to have this one sort of induced or reduced to this coefficient, to e to power I theta. So we have something like this. So this is still shows us the movement on the Bloch sphere, but it's in an indirect way. So it's because this one is actually cosine theta plus I sine theta. So if I can design a problem where I can compute this theta, I'm pretty much can get the vector on the Bloch sphere. So the location of the vector will represent for me the eigenvalue. So it's only the trick is to find this theta. So if I do this now, if I have an eigenvalue problem, because this is one could be diagonal matrix.
And the eigenvalue is the phase, right?
Yeah, this I can represent it as a phase. So if I can succeed, if you want to get the eigenvalue of, for example, MS or energy eigenvalues of molecules, and then you want to compute them, you can tell, okay, this E1 will be e to the power I theta 0. E1 will be E2 or I theta 1. This is E1. This is E0. Then if you compute this theta, you evaluate, you get this energy. And this theta is just a location here. It's just a location of this the vector on the Bloch sphere. Because it's a relative, it's related to the relative phase. So we got this one as a relative phase. It's not a global. If it's a global phase, I can omit it. It doesn't impact my state, but it's a relative phase. So it can it contains quantum information because all quantum information are stored in these amplitudes. The relation between the bases to one another. So the relation between the bases to one another is actually what has the information. This is why we have 2 times in quantum computing. We have the coherence time. So if we have the coherence time, which we call it T1, and we have the dephasing time. We call it T2. The coherence time, it means that how much this quantum state lives, how long, for how long can it live, and if it destroys, it's destroyed, and the dephasing time, how much is this phase, this information, the relative phase between the bases in one qubit, it's just 0 and 1, is intact and preserved. Once it dephases, so this one is no longer sharp, is no longer sharp in value, then it means that the dephasing is happening, and then I'm losing information. So I can still have the coherence, but the information that's stored in the ratio is lost. So that's why there is these 2 times, and of course they are related. So the dephasing time is related to the coherence time, and both of them have to be. So the coherence, because a lot of people care more about the coherence time, but you can have a quantum state with very long coherence time. But the second question is, how about the dephasing time? Can you still retrieve the quantum information or not if you do an error mitigation? So can the error mitigation strategy retrieves for you these phases or not?
So implicit in that remark is if your dephasing time, your decoherence time is too quick, it's going to be too fast to measure, and so that data is going to be lost. That what you're trying to measure. Is that what you're implying?
Yes, you will lose the quantum information, but your quantum status is still alive. So
yes,
the quantum state is still.
But if the information is lost, then I mean it's immaterial at that point, isn't it?
Yes, definitely. But I mean, sometimes when they talk about those metrics, they should indicate that we have 2 times. It's not only the coherence time that we care about. We have another one, but they omit it in discussions as if it is not important, but it's really as much as important as the coherence time, because it has a value of the information is there.
Right. I mean, well, if you can't capture that, then I mean, who cares? I mean, you can be making $1 billion, and if you can't use it, I mean, so what?
Yeah, definitely. Yeah, and now, for example, the dephasing time is related actually to the coherence time. So they are related to. I mean, there is upper bound between both, and if you have a quantum state where you can still measure before the dephasing time, then you can retrieve the information. But if the dephasing time is too quick, then the coherence time will not help you because dephasing is already happening. So, and this is also actually related to the broadening of energy, Heisenberg uncertainty principle. So the uncertainty principle is saying that you have delta E, delta T is actually related to h bar, I think h bar over 2 or something like less than over 2, something like this. And it means that if you, for example, your energy is sharp in energy, then the lifetime, this is a lifetime, is infinite. So for example, if you get one specific energy, 1 electron volt, virtually you have infinite lifetime. But because you can't get that, you get a broadened energy, you get energy with an error in the measurement, then you have upper bound on the lifetime. So the lifetime of a particle is actually related to the energy broadening of this particle. And if you look at the quantum state, how much you can preserve the energy intact. And the energy means that the phase information is related to the phase information. So if the phase information is sort of this information here happening too quick, the dephasing happening too quick before even the time that's used to make the measurement, then that's a huge loss. So this is why that's also an important metric in this, and typically the energy consumption of quantum computers sometimes comes from this relation. How much power you need to supply in order to keep the energy of the system sharp without getting broadening with time.
Thanks. That helps with that.
Yeah, there's a lot of metrics in quantum. Yeah, but only the only dominant one is the coherence time, which is not typically. I mean, there is other metrics that also impact the quality of the quantum hardware. So if you get an infinite coherence time, but then the dephasing time is too quick, then okay. So yeah, is there any question? Yeah, so if not, then I leave you with Abderrahman to present the notebook. So thanks everyone.
Okay. For our notebook today, okay, great. We need to import most of imports we have done it before. We will not add anything new. We will use the QFT that is built in Qiskit library itself. We will initiate two simulators, one for the ideal air simulator, and I have been using fake Sherbrooke as a noisy simulator built in Qiskit fake provider. Okay, these two functions we have used them before in all the previous sessions, so it's the same. Here it's new. We define a controlled phase gate. As Dr. Taha said, phase gate, it's a gate that applies phase e to the power e to the I theta. Then it's a controlled, so it's an identity 0, 0, and the gate B itself. So it's applying phase in case of all ones in this case. So how to find it? We define a circuit of 1 qubit. Then we apply this B with 2 to the power. We can maybe draw it. It can be the theta here will be 2 pi times by eigenvalue. We can say eigenvalue, I can say it's theta, and this is maybe alpha. Yeah, like this alpha, yeah. Times k. So this all in the power itself. So e to the power, all of that. 2 pi. The eigenvalue is between 0 and 1. And the k is the number of times the gate has been applied. So after all of that, we apply one control. So it's control B. Then we can convert it to a gate. So it's that's all. We can convert it as a gate. So we can call it after that, yeah, control phase takes the eigenvalue and the k, how many times we want to apply it. Or the QPE itself, it takes the eigenvalue and number of estimation qubits. We'll see how it's differ for the if we choose different numbers of estimation qubits. We define a circuit. the estimation qubits plus 1. This is the auxiliary which will do the phase kickback for us. And for the classical register, which we need just only a number of estimation qubits. Okay. We apply Hadamard for all the estimation qubits. Then for our auxiliary, we'll apply NOT gate so it can do the phase kickback phenomena. Then for each qubit, we will call a control phase with eigenvalue and the new value of k. Then we append it. We call it here control C with the qubits that so it's like maybe I can show you. I have printed so it can be clearer. For 2 qubits, it's like that. Yeah. For the first qubit, then apply the gate with the control. Then second qubit is the control. Then exit. Okay. For the Q of t part, I have used the Q of t built-in function. But in our case, in QPE, we need the inverse. So we call the Q of t with the number of estimation, and we do the inverse. So it's apply the inverse of Q of t, which is inverse quantum field transform. Here I do swaps. I set it false as the ordering in Qiskit is reversed for our case. So if for Qiskit, they start counting from the right, so it's first qubit. So if it's I have 3 qubits here, the first qubit here is from the right, and second qubit after that, yeah. But in our analysis and most papers, it's reversed. So the first qubit actually starts from the left, which called MSB, most significant bit. But in Qiskit, it's least significant bit, so it starts from the right. So in our case, for the quantum field transform, I have disabled the swaps. Then we do the measurement. Okay. For the running itself, takes the eigenvalue, number of estimation qubits, number of shots, and do I want it noisy or not? Build the circuit and initiate the backend. If it's noisy, and then I call the function for running and plotting the counts. Start here with only 2 qubits. So if I like to represent it, if I have 2 qubits, then I have 4 stations. 0, I have from 0 to 1. Then I have the first station, which is 0. And then 1/4, which is 0.25, and then half, 2/4, then lastly 3/4. So the estimation can be done for eigenvalues 0, 1/4, 2/4, 3/4. If I want to increase the precision, increase the number of qubits, if it's 3, then I can divide this number of this spectrum to 8 parts. So it's 1/8, 2/8, etc. So the number, if I put like 10, it will be divided into 1000 parts, etc. Yeah. So number of qubits here, if I increase it, the precision will be increased. And this is the trade-off. The number of gates will be numerous, and it can be done without any noise. Yeah. So 2 qubits, and the eigenvalue I want is 1/4. Circuit and counts. After running the circuit, I will see I have get 100% 0, 1. Okay, 0, 1 here. 0 is mapping to 0, 0, and 1/4 is mapped to 0, 1, 0, 1. 2/4 is mapped to 1, 0. 3/4 is mapped to 1, 1. So after the measurement, I will see that I have got 0, 1, which means the eigenvalue must be 1/4. This is how the estimation is done. So maybe we can try, for example, 3 qubits with the same eigenvalue. I will see I have got 0, 1, 0, which is, we can maybe do this. 0, 0, 0 is mapped to 0. 0, 1, 1 is mapped to 1/8. 0, 1, 0 is mapped to 2/8, which is 25. Yeah. So it's this is a binary representation. We do it to a decimal representation. So 0, 0, 0, 0, 1 in decimal is 1, and divided it by 2 to the power of qubits. So for example, if I have got 110, which is 6 divided by 2 to the power of qubits, which is 3. So it's 6/8, which is 75 out of 100. Okay, so this is my eigenvalue. This is for the ideal scenario. This is the circuit, 2 Hadmers and the NOT gate, the control phase gates, and the inverse quantum free transform and the measurement. I then compose it to, we can see the gate cell. We don't care about the two. This is the phase, control phase, and this is the inverse of quantum free transform. We have discussed it last session. Okay. For our noise simulation, we'll see that it's, because if it's a little number of qubits, it's kind of resilience of noise. So it's pretty much like the ideal 0, 1. Maybe we can increase number of qubits. Let's say 10 qubits. It will take much time. And let's say a random eigenvalue. Let's say 33, for example. Run. Yeah, I will get, let's see, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1. We can maybe convert it to decimal. Just give me a minute. 0, 1, 0, 1, 0, 1, 2 zeros, and 1 0, is it? Yeah. 0, 1, 2 zeros, 1 0. 2 decimal. So this binary number to decimal, it's 338 divided by 2 to the power number of qubits with 10 will give us, just give me a sec. Okay, 3 divided by will give me 0.330078, etc. So it estimates to a certain degree the eigenvalue that I have entered as an input. So, and the circuit will be much bigger if we maybe the decomposed circuit will be enormous. Yeah. Yeah. It's, okay. Okay. For the noisy part, we can see, but if you take a closer look, the maximum number, it's only 800. So when we increase the number of qubits and there is noise, it doesn't give us the correct answer at all. So that's one of the problems of the quantum phase estimation is, as Dr. Taha said, the decoherence, dephasing, and increasing the number of qubits. So this is for the practical lab today. If there is any questions, may ask. So there is no questions about the lecture, the practical lab, anything. Okay, great. We'll conclude the day for now and see you next week. We'll be discussing the Shor algorithm. Yeah. For the material for the sessions will be uploaded to the YouTube playlist, and for the notebooks and lectures will be uploaded to the repo GitHub. All links in the LinkedIn post. So if you have any questions, you can ask privately or contact Dr. Taha or contact me. There is no. Okay. Okay. See you and have a nice day.